Thank you. I really appreciate Jesus and Roland for inviting me to give this talk today. Also want to extend my gratitude as well to Harvard for taking this on under dire circumstances. It's good to be here at this workshop. I'm really appreciating the time here, being able to learn from you all, and look forward to a few more conversations over the next couple of days. I'm coming to you from the University of Maryland. I'm in the chemistry department there, and much like we just heard Jim do, I want to give a little bit of sort of introduction to my perspective on the science we're talking about today. So I studied cold chemistry in the chemistry department at Maryland. I started my group there in 2019. We got into the lab in spring 2021, and then really have things rolling now in the next few years after that. As I said, I'm a chemist, and my perspective on the role that chemistry plays in a field like AMO physics is that we are giving you opportunities for applications of all of the groundwork that you're doing in developing new techniques and that we can apply in the laboratory. So I'm here in the center, and we are applying the techniques that you've developed. I also view, this sort of growing pyramid of foundations where math sort of builds the basis of this scientific enterprise that we're all together on. Physics builds on top of that, chemistry builds on top of that, and then biology builds on top of the rest of us. So we really have this groundwork being done here, although unfortunately the funding agencies don't necessarily view us in the same perspective, although I'll say those are 2023 numbers, so who knows what is going to happen next. And I also want to kind of set a stage in terms of the way I view chemistry. So this is a graph I use when I teach general chemistry to pre-meds. This is the familiar Arrhenius chemistry, where we're determining canonical rate constants based on transition state theory, where our rate constant is going to be determined by the activation energy, the barrier height, the temperature of the reaction. And so from an Arrhenius perspective, as the temperature goes up, the rate constant is going to go up. Of course, I actually want to mention that Arrhenius was actually a physicist who won the Nobel Prize in chemistry. But he himself said that biological chemistry cannot develop into a real science without the aid of the exact methods offered by physical chemistry. So here I am today as a physical chemist, sharing with you my interest in the chemical reactions that actually have an opposite effect. Instead of the temperature dependence raising the rate constant, it actually results in lower temperatures. This is not a surprise to the people in this room because you're all familiar with how sensitive collision cross sections are to temperature, but it is something that quite surprises my chemistry colleagues. I also kind of want to give a little bit of perspective on what I mean by cold chemistry. I know there's some more strict definitions out there for what would actually constitute cold. I prefer this sort of more general term defined by Strecker and Chandler, where they're showing that it's really when you start to see exotic phenomenon that can't be explained sort of using normal statistical ensemble measurements. That's what we mean by cold chemistry. And I really like to apply this sort of thinking, a more broader thinking than like a hard 1 Kelvin cutoff. So with all that perspective in mind, I also want to tell you about sort of what motivates people in my group, and that's astrochemistry. Here we are in CFA. And this is showing what I find really exciting about astrochemistry, because you have this amazing diversity of environments that you have to take into consideration when you are studying astrochemistry. This is just for molecular clouds, where I'm interested sort of in the density and temperature ranges that you can experience under these different astrophysical objects, just within the category of molecular clouds. So the densities range wildly depending on whether you're in diffuse or dense clouds. And then the temperatures also scale quite a bit. And so none of these probably would fall under the sort of the umbrella of cold chemistry by the physicist definition, but the exotic chemistry that happens under these temperature conditions in space, I think, is really pushing chemistry forward to thinking more creatively about how reaction mechanisms proceed under these extreme environments. My group's not the first to think about this sort of thing. There's been plenty of laboratory efforts over the last few decades to study chemical reactions at the low temperature regime that's relevant here to space. So I have a lot of different directions in my research group. I'm not going to talk about all of them today. I'm just going to focus on this top quadrant here, where we're using buffer gas cooling techniques to study molecular spectroscopy at high resolution. This is work that was led by Thomas Howard, who just finished his thesis last month. He had a few collaborators over the years and is now being taken over by Tucker Forbes, who's a new first-year graduate student in my group. So we're motivated largely by, in this part of my research group, by the new spectroscopy techniques that are capable, that James Webb Space Telescope has made possible to us. In particular, I think one of the really exciting things about James Webb is that they're going to be able to use they are using transmission spectroscopy to study exoplanetary atmospheres. Not only does this give us access to really amazing, unique chemistry that is otherworldly, it also is a really exciting field that students get really jived up about. But I just think it's incredible that you can actually go and measure the spectra of the atmospheres surrounding exoplanets in these techniques. And one of the things that I find really interesting also is that James Webb has enabled us to access spectroscopy regions that have not been heavily used in astrophysical observations in the past. The near and infrared regions of the spectrum are the planned sort of tools to be used in a lot of these exoplanet detections. And so James Webb is allowing us to has improved detection sensitivity. What that means is you can detect lower and lower concentrations in these environments. And what comes with that is you can see more and more stuff. Anytime you turn up your detection sensitivity, you make your life more difficult because you have more molecules now that you're observing that then you have to understand how they're being formed and how they react. So I'll give an example. Cyanoacetylene is one of our favorite molecules in the group. This is a fundamental building block in the RNA world hypothesis, where the pyrimidine ribonucleobases are formed directly from cyanoacetylene as the starting material. So here's cyanoacetylene for those of you who don't remember your organic chemistry. It is not only a fundamental building block for RNA world hypothesis, it's also a signature for other types of exoplanetary activities such as volcanism and, lightning signatures and impact signatures as well. And that's what's shown here on this graphic here, where they're indicating the different spectral regions that they're targeting for detection of cyanoacetylene using James Webb. And something I notice as a spectroscopist is they've left behind the near infrared region in this graphic. And this is notable to me because the near infrared gives us access to cheap, of course cheap is a relative term, lasers and all of the corresponding technology that has been built up around the telecom region. So why is it that this region has been left out of the sort of estimates for detection of cyanoacetylene? And what can we do to fill this gap? So our goals in the lab are to assist with laboratory data that can be used to understand spectroscopy for astrophysical applications, as well as ultimately doing low temperature chemistry by preparing our reactant molecules at the low temperature conditions that we would need. So the spectroscopy is made more possible if we can have our molecules at low temperature as well. So that kind of goes hand in hand, both the reactivity and the spectroscopy. We would need low temperature molecules for those. So this is where we've taken from the physics world the tool of buffer gas or sympathetic cooling, collisional cooling. Many of you are familiar with buffer gas beam sources. They are a great low temperature, temperatures down to sort of the 4 Kelvin range tool. They tend to be in the lower pressure range, so sort of in the 1 torr range is the bath gas pressure in buffer gas cells. And so this is notable to me because I'm interested from a spectroscopic standpoint to reduce the possibility of collisions happening. That helps us clean up our spectroscopy a bit through reducing pressure broadening. It's also a very general sort of generic source, and so you can kind of use it for a lot of different molecules. This is what it looks like in our lab. It's basically a copper box that's attached to a helium cryostat and surrounded by radiation shielding. We started out by studying hydrogen cyanide. It's a benchmark molecule. It's a wavelength standard in the near infrared, so there's a lot known about it. It also has a high vapor pressure, so just logistically that makes it easy for us to work with in the lab, and it has its own relevance to astrochemistry. The downside of hydrogen cyanide, besides it being a chemical warfare agent, is that you have to synthesize it yourself. Those two actually might be related problems. So we did that in our lab. We synthesized hydrogen cyanide from dropwise addition of sulfuric acid to KCN. That's what we set up this system in our lab. So we just evolve off the HCN and collect that. So it's a really actually great way for us to make hydrogen cyanide because it enables us to prepare mixtures in whatever bath gas we want to study, whether we want to study HCN and helium or argon or H2 or whatever bath gas, we can prepare it in that way instead of having to buy some custom mix from a Matheson or whatever. To study the spectroscopy of these molecules, we use cavity ring down spectroscopy that enables us to operate at really low densities because it's a very sensitive, high resolution method. We are probing specifically the CH overtone stretch of HCN. This is, as I said, in the telecom region. We have Doppler broadened line widths, so we can actually, at these low pressures, we're able to actually observe those line shapes directly. And then we can operate at pretty low HCN densities as well. We're very sensitive. This CH overtone actually has a kind of anomalously high cross-section, absorption cross-section. We do CW CRDS. We have a continuous wave tunable diode laser that we use for our spectroscopy, and we couple that into an optical cavity. Here, this example is just our room temperature cavity. For now, I'll show you in a second our buffer gas cooled cavity. Again, at room temperature, this is the HCN spectrum, the first one that we collected. We observe both the P and the R branches of HCN in this vibrational spectrum. We can also zoom in at any one of these row vibrational lines and observe the line shape here. And by fitting the Gaussian to this to our data, we can obtain the Gaussian profile and report the translational temperature. And not surprisingly, our room temperature hydrogen cyanide has a translational temperature of room temperature. So that worked out, that's great. We also can use the rotational spectroscopy to measure the rotational temperature of the molecule. And using Boltzmann statistics and Hertzberg, we can show using the peak areas of those lines that our rotational temperature is also room temperature when our molecules are at room temperature. So none of this came as any surprise at all. This was sort of just building up our new instrumentation and developing the techniques to do these molecular thermometry measurements. We then took our nice stable optical cavity and slapped a rotating or vibrating, shaking piece of mechanical equipment into the center of it and put our helium cryostat right in the middle. This allowed us to then have our buffer gas cell in the center of our optical beam path, and we can then measure the molecules that are being probed inside that, buffer gas cell. So we simply drilled holes through everything, through the outer heat shields, and then the buffer gas cell itself. So this is the Heaney laser that's shining through. And so that allows us to cool our molecules down. So now we're down at 150 Kelvin. This is still hydrogen cyanide. And so you can see the spectra are starting to get more clean. We don't have as many hot bands still present in the spectrum. And our rotational temperature and translational temperatures can be measured as well. So this HCN line we fit to also 150 Kelvin translational temperature, and then the measurements of the rotational temperatures at the various buffer gas temperatures are also thermally equilibrated. So we showed for hydrogen cyanide that we can cool the molecules down to 150 Kelvin. That buffer gas cell is at 150 Kelvin, and the translational rotational temperatures are as well. So that was great. That was hydrogen cyanide. This was a molecule that we wanted to sort of cut our teeth with in the lab and make sure that we had all of our techniques worked out. Now we wanted to go and do cyanoacetylene because this was the molecule that was very interesting from the RNA world hypothesis. It's a larger molecule, so that comes with it a smaller rotational constant. That gives us some additional challenges in spectroscopy because now the lines are going to be closer together, and so it's a challenge for our laser resolution, and it also results in more congested spectra. As we get bigger, also, we start to have these low frequency bending vibrations be more likely to be excited. And so we also need to make sure that we are cooling our molecules down, so we're not including those in the pure spectroscopy of the CH overtone vibration. We also had to do synthesis again to do cyanoacetylene. This is a very dramatic video made by my grad student who, I guess, took some artistic license in showing you our synthesis setup. So we again had to synthesize the cyanoacetylene. In that case, we had to adapt our synthetic protocol for a gas phase synthesis. We also wanted to go colder. So you notice with the hydrogen cyanide, we only went down to 150 Kelvin, but buffer gas cooling we know can get to at least 4 Kelvin. You've got your helium cryostat. There shouldn't be a reason why you can't go that cold. The other reason why we needed to go to colder temperatures is because with this heavier mass, we now also have more narrow spectroscopic lines. For the spectroscopists in the room, you probably noticed that our Gaussian peaks were definitely undersampled in the HCN 150 Kelvin data. We were not taking steps that were small enough to really do a good job of measuring the line shape of HCN. So we definitely needed to improve this if we were going to do low temperature cyanoacetylene. So Thomas was able to do that. He made several improvements to the spectroscopy apparatus. And then the result was that we were able to get to 20 Kelvin cyanoacetylene with good sampling on our peak. The residuals, in case you also noticed those, the residuals are much smaller now too. So we're just generally improving everything about the spectroscopy apparatus with these updates. And so this is cyanoacetylene at 20 Kelvin, and indeed the translational temperature was 20 Kelvin there. So that allowed us to measure the full rotationally resolved CH overtone band for cyanoacetylene. We were able to report this in the literature with high resolution for the first time. And that also enabled us to report the vibrational excited rotational constants for this molecule to contribute that to sort of the HYTRAN and spectroscopy world's database. But going back to this question of cyanoacetylene in exoplanetary atmospheres, is this a potential target now for cyanoacetylene detection in exoplanetary atmospheres? I pointed out that there was no data in the telecom region for cyanoacetylene detection in exoplanets. And so this 1.5 micron detection of cyanoacetylene would fill this gap here. So that would be where we would propose to see it. And there's been some past studies, some recent work showing that there are some other biosignatures or volcanic signatures that could be detected in the 1.5 micron region. For example, H2S is suggested to be detected. And so we looked at this sort of region of the near spec estimates and sort of use this as a ballpark for whether we would have the detection sensitivity to see cyanoacetylene here. And it turns out that the band strength for hydrogen cyanide or cyanoacetylene that we measured in the lab is like an order of magnitude larger than H2S. So we would propose that as a potential target for this region, since they certainly expect to have plenty of sensitivity to see H2S. So that was our suggestion, is that they can add the 1.5 micron region as a place to look for cyanoacetylene. So that was exciting. All right, so that was what we set out to do with the buffer gas cooling instrument. So we were very successful in building this high resolution, high sensitivity instrument. Thomas was successful with coming up with an acronym for it that actually worked. And I think one of the things that we really found sort of pleasing about this was that it worked. You know, we put this, shaking cryo head in the center of an optical cavity, and we maintained our spectroscopy setup through all of it. So that was kind of a pleasant surprise to me. And we can go pretty cold. So that 20 Kelvin limit is just sort of based on the fact that we do have to flow our gases into the cell. We're not doing a lot of pre-cooling because we lose a lot of our molecules if we do pre-cooling on our lines. So we can't quite get to 4 Kelvin, but for our astronomy friends, I think 20 Kelvin was reasonable. And we were able to move on to larger cyanopolyions. So what's next is we're thinking about ways to adapt this instrument to do new science, thinking about pump probe techniques and other ways of producing non-equilibrium systems. So that was when I met Jesus in November. And I was talking to him about our buffer gas instrument, and he suggested to me, have you ever thought about studying clusters in your buffer gas cell? And I said, well, not really. And one of the reasons is because, the introduction of the chemical review article on buffer gas cells says explicitly that the density is low enough to prevent simple three-body collision cluster formation. But, we're experimentalists, so let's try it. We'll see what we can do. One thing we have going for us is that HCM has a pretty large permanent dipole, pretty large permanent polarizability. So, maybe we can operate with the right molecule, maybe we can get lucky. So that's what Jesus suggested to us, and he specifically told us to look for line shape effects. So this is, again, it's a challenge to our instrumentation. As you saw, we needed to think about improving our resolution and our signal to noise. And if you're going to do line shape studies, then you have to have really good signal to noise, really good resolution. So that was sort of the challenge now, is to continue improving our spectroscopy apparatus so that we can do that. It also worked out really well with timing because Thomas was graduating and Tucker's coming in. And so it was a great opportunity to kind of shift focus and see if Tucker can keep the instrument running through these tests. So that's what they did, is they went and improved our resolution and signal noise further. And now I'm showing you the spectrum of HCN. So I'm back to hydrogen cyanide. This is HCN with a very high resolution measurement, very good signal to noise, and I'm blowing up for you the residuals here so you can evaluate those for yourself. So it's a pretty good Gaussian fit, but certainly improvements could be made with different line shape functions, but it looks pretty Gaussian, pretty symmetric to me. And this is in pure helium. So then based on what Jesus recommended to us, we started doping in argon into our bath gas. So removing some of the helium and swapping it out for argon. And so you would expect that if you form a complex, you'd form this linear structure with the argon, more likely to, based on the interaction potentials, to be on the hydrogen side of the molecule. And based on the spectroscopy now, this is the comparison of argon, 20% argon with pure helium. So orange is the pure helium and blue is the argon. And hearing from above that Jesus suggested to us to look for broadening in the wings. You can kind of squint at this with loving eyes and start to convince yourself that there's something going on this lower energy tail, possibly. Another notable feature is that the peak intensity has dropped a little bit. So these are some things that we're throwing at Jesus, who's right here staring at our data. But I think that one of the things that we really have to think about is how accurately we can measure how precisely we're making these measurements, and whether we're just over interpreting our data. So Tucker's back in lab, continuing to study this again. But for now, I'll just compare for you the residuals between 0% argon and 20% argon. To me, they both look pretty Gaussian, so I'm not really sure if we're just over interpreting our data or not, but we've got more data coming, and we'll see how it goes. So that's sort of where we're at right now. We're kind of curious if there's other molecules that we could study. So one example would actually be cyanoacetylene, which you already know we can study in our instrument. It's got a larger permanent dipole moment and a huge polarizability. But I will say that this is an artist's rendition of how the argon would likely be bonded in the complex based on the interaction potentials. It's actually more likely T-shaped. So I don't know what this would do in terms of the theoretical perspective on the complexation and the line shape studies. So that's where we're at. And I will just finish up by talking a little bit about the other projects. I just want to mention the goal with producing the cold molecules is so that we can do low temperature ion molecule reactions. So we have an ion instrument in the lab that we're hoping to use for kinetics. We also are interested in the weakly bound complexes that form and studying also the nuclear spin enrichment and nuclear spin conversion processes that can happen in weak interactions. So that's what's going on here. And then we also have another branch of our lab that studies photodissociation and some general kinetics for astrochem applications. So with that, I will acknowledge that the work I talked about today is funded by the NSF. And I want to give a shout out to Thomas Howard. He just defended his thesis last month, and due to some federal funding shenanigans, is looking for a job. So I really hope that if any of you are looking for a really, really awesome, skilled instrumentalist who's a phenomenal research mentor, Thomas is your guy. So please talk to me if you have postdoc or job opportunities available, because he's great. So with that, I will happily take questions. Thank you.
Thank you very much. Who wants to start? Yes.
Two questions. The first one brief. So you measured the P and R branches in cyanoacetylene. Can you extract the dipole moment?
The dipole moment?
Mm-hmm.
You
mentioned there's a large dipole moment, 3 point something.
Yeah. I mean, we assumed that was known. We didn't solve for that. No.
So the second question is about this. This collaboration about cluster formation. Have you actually measured the recombination rate?
No, we're not doing dynamics here. So this would be purely spectroscopy. So at this point, we're looking for evidence of cluster formation from the spectroscopy alone.
So because the reason I mentioned is about 15 or so years ago with John Doyle's group, you know, over here in a helium buffer gas, we actually were able to measure, and I did not do the measurement, I did the calculation for the formation of these van der Waals silver helium molecules. So we actually measured the rate for the combination.
Other questions? Yes.
Could you give some intuition as to why the binding of the noble gas atom leads to broadening of your rotational lines?
I mean, I don't think it's, from what I understand from talking to Jesus, I don't believe it's a pressure broadening mechanism, because the pressure broadening coefficients in this spectral region it's like half a wave number per atmosphere. So this is not going to be a pressure broadening sort of classical mechanism. So I will leave it to Jesus to maybe explain where the asymmetric line function comes from that he's looking for in our data. I
guess my maybe another way to ask my question is, do you expect the argon to be rigidly bound to the molecule, or is this still like a free rotor that's rotating in the vicinity of this argon atom.
I would think that the binding energy is sufficient that it would stay bound, but that's a good question.
It could likely form a van der Waals type.
I just have a quick question. How fast can you scan? Because I guess for the HCN you had to scan
Yeah.
to find the lines. Was it like
Yeah,
fast or?
yeah, so there's like long spectra that you see, the survey spectra are like hours, like 8 hours to
so
do the full
fast.
spectrum. What I didn't mention here is we are actually not locking our cavity. So we are sampling really inefficiently at this point. So Thomas is back in the lab right now trying to lock our cavity is what we're hoping to do in the future. But it's actually we're free running. And so we scan how fast as we can stay resonant.
No, because once you have your cluster, it will have a different frequency, of course, so you have to scan again.
So I allow myself some questions. So first of all, do you also see combination bands with these low frequency bending vibrations? I would think that would be very interesting.
Yes,
right?
yes, I agree with you. Yeah, from a
In the of course in the
Right.
HC3.
right, yes. When I didn't show the room temperature spectra for cyanocylene, but there's definitely a lot going on in the room temperature spectra. There's certainly combination bands. I agree with you. I think that the bending modes are a really fascinating aspect of these cyanopolyions. So it's on our radar for sure. But we wanted to get rid of them for the purposes of reporting the overtone spectroscopy.
And maybe the other question, do you see effects of the concentration of the HCN or also of the HC3N in terms of the line shapes? I mean, you look at argon as having an effect, but I mean,
Yeah,
if you have a high concentration of HCN
Yeah.
with its polar
Yeah.
dipole-dipole interaction,
right.
you may also see directly a shift or some interaction. with the
Yeah.
lines.
Yeah, we've tried to keep things as low as possible because we really do want to avoid we're trying to avoid those interactions. So you're right. I mean, we could cause them,
Yeah,
but the other challenge we're always fighting with is losing our molecule of interest to the walls, because it's just
Sure.
if a hydrogen cyanide hits a 20
Yeah.
Kelvin wall, it's going to stick.
I'm just thinking the interaction must be so much stronger that maybe it's easier to find.
Yeah. I mean, certainly, yeah. But then we would lose all of our buffer gas cooling. So
Yeah.
it'll be sort of a give and take with that. Yeah. So I agree.
Any further questions? Yes.
So, you know, one motivation was people look into outer space and they look at these exoplanets and the atmosphere. And I was just wondering, so what can they resolve? Do you know a little bit about this? Or what is, how can you well identify a particular molecule that you have to particularly cook up in your lab?
Yeah.
What are the chances, and are there certain frequency or frequency bands that are just so crowded it's hopeless? I don't know.
Yeah.
If you could just tell us a little bit more about that.
Right. Yeah. Well, I mean, it really, one thing is that the one limitation right now of even what our application of our study is that the exoplanets that they're observing are all really hot atmospheres because they're all really close to their star because they're being observed in the transit method. And so any of the molecules that are observed using transmission spectroscopy are in hot environments. And so my 20 Kelvin spectrum is not going to project very well up because the rotational states don't really stay, well reproduced in that way. So your first question was about resolution. So they don't have rotationally resolved resolution with most of these measurements. And so what you're looking at is the integrated band strength. And so what we're comparing here is the integrated band strength, and whether that's spread out over 100 rotational lines, then that would smear it quite low. So they can resolve, that there's a vibrational band here. They definitely have that level of resolution. But whether they can't do what we do here with the individually resolved J states. I guess your other question was sort of what spectral regions get kind of crowded, and I think it just depends on what kind of environment it is. If you have a an atmosphere that has a lot of water in it. Water is this huge absorber across the wide range of the mid-infrared, and so if you have a planet with a lot of water on it, you're toast if you want to try and see, resolve anything else. But on planets like these Hycean sort of worlds, it seems like it's more organics. And so ones that are low in methane, I think are good targets for, it's good to move away from spectral regions where there's a lot of methane, I guess is what I'm saying. I don't think I fully answered all of your questions, but
Two just really quick questions. For one, you said you might do a probe in the future. Would you have to get rid of the cavity? Because you can't really do both at the same time.
the cavity can be, I would not want to send like a UV laser down through our mid-IR cavity, but we could go perpendicular or next to. So I think we have a few designs in mind. Yeah.
In that case, if you do a probe, do you know what when the structure binds with argon, for instance, what's the lifetime in your cavity / cell before it flies
Yeah.
off?
So like the diffusion time inside the cell is sort of on the order of like maybe 10 milliseconds. So it doesn't have a ton of time in there. But it's, depending on, you just have to pick the right dynamics to study.
All right. I don't see any further questions, so let's thank you once again.